support tickets. We have, I think, a database of about 4,000 of them. What we want to do is build a system that will automatically respond to these tickets. So we're going to keep enhancing it so it gets better and better at responding to tickets. We haven't really responded to any yet. We've done sort of classification. We've used an LLM to translate them from 4 or 5 different languages all into English, because we determine that's what our support team speaks. So we want everything coming in to be translated from whatever language they were sent in into English. We did that. We are now going to start getting our toe in the water in actually automatically responding to these tickets. So that's what we're going to work on today. So here's kind of our RAG pipeline. If you remember from a few weeks ago, we took a PDF, we chunked it into chunks, and then we used an embedding model to summarize those chunks using vectors. We put those vectors as keys, and then the document chunk itself as the body into a vector database. So if you recall, what the vectors are is an encoding of the meaning, the semantic meaning of the chunk of the document. And that allows us to then take a user query, run it through the same embedding model, generate a vector, and then using what's called cosine similarity, we compare the vector from the user query against the vectors in the database. We return some number of chunks of text that are similar to the user query. So if we have a bunch of stuff about the Cisco 732 router in our database, and the user asks a question about the Cisco 732 router, presumably those will match up, and we'll get a bunch of chunks of text about the 732 router, which we can then combine, give it to the LLM as context. We give the user query, why won't my 732 router do this function? We give it the context of the closest chunks that match that. We feed that to an LLM using a prompt, just like you would write your own prompt with a chat bot, and then submit that to the LLM and have it generate an answer. So what does that get us? It gives the LLM very specific knowledge that it may not have. These documents could be user manuals, FAQs, troubleshooting guides. They could even be past tickets that we've already answered and have been judged to be good answers. So we have the potential for feeding a lot of knowledge in and then telling the LLM to use that knowledge so that it grounds it in reality. We all have heard about hallucinating LLMs. This is a way to counteract that. We can tell the LLM to use this knowledge instead of its own general knowledge. So the LLM, if you think about the LLM, it kind of has 2 superpowers. One is it has memory. So from its training data, let's say it's trained on everything in the internet, it's got a lot of training data. And in there somewhere is stuff about the Cisco 732 router, mixed amongst all kinds of other stuff, Python code, jokes, memes, complete falsehood, political arguments. It's all in there. So if you want to think about an LLM in one way, it's taking all of that training data and compressing it into a small space. So you take 8 trillion tokens on the internet and you compress it down into 20 billion neurons. Chances are things get a little bit mixed up and muddled. That's why you sometimes get hallucinations. So giving it specific context that's relevant to the query really helps sort that out. The other superpower it has that I would argue is an even a better superpower is the ability to manipulate language. So that is, it can translate from different languages to other languages. It can summarize, it can expand on things, it can use context, etc. So this language manipulation capability is sort of separate from its knowledge. And if we give it context and we say, use only this context to answer the question, really all we're using from the LLM is its ability to manipulate language and not its memories, which if you use smaller and smaller models, remember very first class, we ran some experiments asking very tiny models some obscure questions, and they just didn't know, so they made up answers. Then as we got larger, we went from a 1 billion parameter model to a 4, to a 7, to a 20, to 120 billion parameters. The answers got better and better, and the knowledge got better because we weren't trying to compress the entire internet down into a tiny space. The more space we have, the better the answers. It just stands to reason. So again, if you think of LLMs as sort of a lossy compression of whatever the training data is, that's one way to look at it. And if we use a small model, we can often use just its language manipulation capabilities and forget about its stored knowledge, which may be faulty. So again, just reviewing, an embedding is simply using a specialized model that's been trained to translate a chunk of text into a numeric vector. And we use this example where if you think about a vector as a point in space, we can translate a word or a chunk of text into a point in space. And what we expect from standard vector arithmetic is that points in the vector space that are close together are also semantically close in meaning. So if we vectorize all these words, we get points in space where cat and kitten are very close, but they're a little bit further from dog and they're quite a bit further from houses. We can also think about the mathematical implications where we can do analogies in a sense. If you remember, like your standard old college entrance exams, X is to Y as Z is to blank. So man is to woman as king is to queen. The translation, the numeric translation, the geometric translation is very similar between the two because they differ mostly in their gender. So you could think about this as a gender translation in a geometric space. So that's kind of a little bit of review of where we're at. So what I want to do today is just spend more time jumping into the coding because it's a pretty long chunk of code I've got to go over today. And what I want to do is spend most of our time in that. We may not get through it all today, which is fine. We'll just pick up where we left off. So any questions at this point before we go on? Oh, okay. Clean things up here. Let me share my window here. Okay, we're going to dive in. So I've got a week 5 folder. I'll be pushing this up to the GitHub, so you'll be able to download all this stuff and take a look at it. So I've got most of my notes are actually right in here rather than in a slideshow. So you should be able to see that okay, I hope. So recapping, if we go back to week 2, week 1 was mostly just introductory stuff. Week 2, we looked at ticket triage. Our big thing is there, we detected the language of the support tickets. We translated the subject and the body to English, and we classified the tickets into type, queue, and priority categories. And we used individual calls to the LLM for each of those tasks. So it was a very simple process. We just made multiple LLM calls to detect the language, then we translated, then we classified, etc. So we processed tickets one at a time, and in fact, we processed each piece of a ticket separately. In week 3, we consolidated the LLM calls. Instead of all the separate calls, we made one comprehensive call. I'd say the big the big takeaway from week 3 was we were able to create structured output. And instead of just returning a big blob of random text, we brought back structured JSON so that we could easily parse through the return and interpret it as data. So we coaxed the LLM into creating a nice JSON return, and it created a very function-like atmosphere. We could call a function and get a JSON package as a return. Whether it was an LLM behind the scenes or not, we kind of didn't have to care. We got a very nice structure we could deal with. Last week, what we did was kind of deviated from our app, and we just did a quick example of RAG, where we took a PDF, we chunked it, we embedded it, we stored it in a vector database called ChromaDB, and then we generated answers from that. So that's where we were. So this week, we're going to take that same concept and we're going to turn it back to our app. So we're going to take the RAG concept we learned last week and work on it so that it applies to our app. So what we want to do is we have a database of 4,000 tickets. And when you download the GitHub for week 5, you'll see the full thing here. I think in the previous classes, I did sections of 100 or whatever, but here's all 4,000. So you've got the subject, the body, the answer. They're all in different languages. We've got the queue that it was in, priority, business type. There's some other tags that were added. I'm ignoring those for now. And then what I did was I wrote a little routine, which you will have. It's called translate-tickets.py. And it just ran through all 4,000 of these and did the translations so that we don't have to do that within our app, because that takes a fair amount of time. We'll go back to our. So basically, I did the pre-translation for you, and we added columns at the right-hand side of the CSV with English translations of the subject line, the body of the request, and the answer. So what we want to do is basically take those answers and we're going to put them in our vector database. So we have already answered 4,000 tickets. What we want to do is take those, we're going to split this into what I call a training test split. We're going to use roughly 80% of the tickets, and we're going to put those in our vector database. We're going to hold out 20% of the tickets as our test set. We're not going to put those in the database. We'll use that to test our whole process. So in a sense, in machine learning, it's a good idea to have this sort of training test split. We're not technically training, although I'm going to sort of cheat and call vectorization and chunking and putting stuff in the vector database kind of a pseudo training. We'll do a little bit of confidence scoring. We'll evaluate our answers, and then we'll test some stuff. So what we're going to do is we're going to take the pre-translated CSV. We're going to extract the English columns. We're going to take 80% of those. We're going to generate the embeddings. We'll store them in a ChromaDB just like we did. So the subject line plus the body will become the key that we use for the vectorization. The answer will be what we store in the database. So we've got just like we did with the PDF, we'll vectorize and then we'll store the body. And then when we get a new ticket, we'll take the subject line and the body, we'll vectorize, and we'll use that as the key to search the vector database. We'll return the most similar tickets, the answers to the most similar tickets. We'll use those as context. We'll add the question and the context. We'll submit that as a prompt. to the LLM. We'll get back an answer. We'll ask the LLM what its confidence is, and voila, we'll have an answer. Now, the nice thing is we'll only ask those of the 20 that we've held out. So though the 20% that we've held out, those will not be in the vector database. So we can then compare the original answer to our generated answer and see, did we do a better job or a worse job than the people, the humans that answered those tickets originally? So we can do a little bit of evaluation of what we're doing. And I've got a little bit of a twist later, so we've got some things we can try. So our CSV data structure is pretty simple. We're really only going to use the English translations. We're going to use 3 columns: the subject, body, and answer in English. Again, we wanted to settle on a common language so we weren't translating on the fly. And so on. So let's work through our code now. And so the first thing we always do is we do our imports. These are basically the same as we did last week. JSON, pandas for data frames, NumPy for doing some math on the vectors, etc. We've got sentence transformers for embedding. We've got ChromaDB for the database. We've got OpenAI general library for calling the LLM. We've got .env for loading our local environment. First thing we do is we load the environment. I'm going to clear the output so we start fresh. Okay, we've got our libraries imported. So this week, what I did was I moved all of the sort of configuration variables into a Python dictionary, so they're all in one place. So we've got our CSV path. That's where we're going to get our translated stuff. That's just a CSV sitting over here. I already showed that here, pretty simple. We've got our ChromaDB path. Actually, I've already run this, but we're going to clear it out when we rerun it. We've got the training test split that we discussed. So 80% of the tickets will be used for vectorizing into the database. We're going to hold out 20% for our testing. We always use a random seed. Almost all universally, people use the number 42, which is a reference to Hitchhiker's Guide to the Galaxy. If you haven't seen it, shame on you. Because there's many references in coding to the Hitchhiker's Guide to the Galaxy, so you might as well watch it and learn it. There is a test mode setting here. If it's true, it will limit things to the first 100. It's not really needed because we're not going to do the translation here. That's the slow part. Side note, when I ran this, I actually used Grok because it's super fast and relatively cheap. The model I used is shown down here. I'll get there in a sec. Our embedding model will be the same one we used last class, which is all mini LLM L6v2. It's a model. It's not quite an LLM, but it's kind of similar. It's a neural network. Again, it's like the front end of an LLM. Its job is simply to take a chunk of text and create a vector. This particular model creates vectors that are 384 dimensions. And then we specify which fields we're going to use. One thing we can do with the vector database is we can actually include metadata fields. We're not going to use that in this class, so I'll skip over that for now. But in addition, so I've been emphasizing that we start with a key, which is the vector, which is the semantic meaning of the chunk, and then the body of the stuff that we're storing, the chunk itself, the chunk of text. Metadata would be other parameters that we could use to help us search. So maybe we only want to search for priority P1 tickets for some reason. We could refine our search by including that piece of metadata. We'll get to that in a later class. A couple other parameters. If you remember, we have our top K. That will limit the number of chunks that are returned from the vector database. So for right now, we're gonna say, just give us the five closest chunks. And then we also set a similarity threshold of 0.3. Anything that's lower than that, don't return. So for example, if there's only three chunks that get above this, we may only get 3 chunks back, because there may not be enough chunks that are high enough. Maybe we have a product for which we've only answered 2 tickets in the past, and there just isn't enough similarity there. So we may get less than 5. Um, and as part of the homework, I'll challenge you to play around with this top K. See, do we get better answers or worse answers if we take top K and make it, 1 or 5 or 100 or whatever? You can play around with that in the homework. Now, we'll talk about this RAG mode a little bit later when we get into it. Then we have our LLM configuration. This is straight out of all of the last classes, so nothing new there. We're going to use GPT OSS 20B. I found that to be a model that I can run on my Mac laptop. It takes about 12 gigabytes, give or take. And not even that. I think it's more like 8. It takes about 8 gigabytes. So it can run on my Mac laptop, might not be able to run on yours. I used the same model for the language to English translation. I did run it on Grok. I was playing around. It turned out that to run all 4,000 tickets on my Mac Studio was going to take about 6 hours. Running it on Grok sped it up by about a factor of 4.5. So I ran all the translations to create this CSV on Grok. It took about 75 minutes, an hour, 15 minutes, and it cost $1.24. So it was kind of interesting. In fact, I'll show you the usage stats here. So here's my Grok account. I spent $1.24 to run OpenAI GPT OSS 20B on all of those things. And that was approximately 6 million tokens. So not too bad. And it was about, like I said, 4.5 times faster. So you can see it was about 4,000 requests, just a little over 4,000 requests, because I ran a test run of 100 or so. Then I ran a couple test runs, and then I ran the full Megillah of roughly 4,000. So not too bad. Sometimes using a remote model is worth $1. Sometimes it's not. But if you remember back to even the first class or two, we did a lot of alternative models. It's also possible that something like a 7 billion parameter model would even be faster and do the English translation just fine. So we'll run this. We've got a couple other, in the ChromaDB, you can actually, inside the database, you can actually have multiple what's called collections. So for this case, we just named it the ticket reg collection. It's going to be the only one we have in there. In a later class, we'll look at adding an additional collection. We'll also get to re-ranking in the next class. So we'll talk about that next time. But basically what re-ranking does is, let's say you decide to return the 10 closest chunks. You can then submit those to a re-ranking model, and those will, instead of using a simplistic cosine similarity on the vectors, it will do a deeper dive, and it will re-rank them it'll re-rank them into the most relevant order using a more sophisticated model. So there's special models that are called re-rankers, and we'll look at adding that to our workflow and see if and how much it improves our results. So with all that said, we're going to proceed with these parameters. Now we'll load. We're loading the embedding models. loaded our all mini LM L6V2. There's many different embedding models. This is a very simple one, very small. It only returns vectors of 384, easy to deal with. Most of the models, most of the more modern embedding models, especially ones that you want to use for larger pieces of text, will return vectors that are more like 1,500 dimensions. So you can fall asleep tonight trying to imagine a 1,500 dimensional space and what that might look like. We initialized our ChromaDB. We connected to LM Studio. This is running locally on my Mac Studio, and loaded the model here. So for the kinds of work we're doing today, the performance of the local Mac Studio is just fine. I could also run this on my laptop as well. Basically, I copied over the stuff from week 2 and 3. These are helper functions, error handling, data loading, calling the LLM, all very, very common functions that we've used basically every week. So I don't think I need to explain anything there. We have our translated data. We've already pretty much discussed this. So I do have this translate tickets.py. Basically, it's just a script. Again, it's calling Grok. It just does all of the translation, just brute force translation of all those columns. So nothing really to get too excited about. So I'm not going to really worry about it in this class. It's essentially the same code that we used 2 weeks ago, just rammed into a single script. So we've got LM Studio connected and ready, so that's good. So now we start getting into a little bit more interesting stuff. Load and split data. So what this function will do is load the data from the CSV, and it will divide it using our train test split and create 2 data frames, a training data frame, which we will use to load the vector database, and a test data frame, which we'll hold out for our testing process. So that will be stuff that's not in the vector database. So we've loaded the data set. There's 3,998 tickets. We run through a simple cleaning process where it removed a few that had empty or missing English translations. For some reason, these failed the translation process, so we're just going to get rid of them for now. Someday we'll go back and figure out why, but it's not that important. We just have to have some stuff to load the vector database. So we end up, after the 80-20% split, we've ended up with 2,880 tickets in the training set or the vectorization set, and the test set has 721 tickets. They're separated into 2 separate data frames. So some of these don't have subjects, but they do have bodies, so we're not too worried about that. And you can see this is just a sanity check to make sure everything is in good working order. So we just did a sample of 3 tickets so that we can see that things look okay. All right. Any questions so far? Looking for hands? No hands? Okay. If you do have a question, throw up your hand. I'll stop. I'll try to check over there once in a while and see if anybody's holding up their hand. All right. So now we're going to set up some functions that do the embedding. First thing we do is we'll combine the text. So we're going to combine the subject and the body of the support ticket request into one chunk of text that will be vectorized. We'll embed that by calling the embedding function, and we'll create a list essentially by iterating over all of the stuff in the training data set. So it'll go through each row of the training data set, it'll embed and create this list. And then once we have that, we have a function to prepare that metadata. Again, we're not going to use that in this class. We're just going to put it in the database. Then we're going to use that list and the metadata to load the vector database. These are all functions we covered in basically week 4. They've just been adapted to the ticket CSV instead of a PDF. So we've got documents, we've got metadata. We're going to batch these into batch of 1,000, and then we're going to throw those into the database. So it's going to go into that collection that we defined. And so let me run this here. So now we've got the functions defined. Now we can actually we're going to do one just as a test. So here's a sample ticket to embed. Dear support, I'm requesting a return for my HP DeskJet 3755. It's not working properly, et cetera, et cetera. So here's the first 10 values of the vector that was generated. And seems like everything's working fine. So now we'll just let her rip on all 2,880. And you'll see just how fast this process is. It's actually pretty impressive. Boom, done. So there's 2,880 tickets that have been batched into 3 batches. They've been loaded, and they're already in the vector database. So we've created the vector, and we've stored everything in the database. Everything's great. The collection, remember, is named Ticket Reg Collection. 2,880 tickets. The embedding dimension is 384 dimensions, and we have these metadata fields. So pretty straightforward. We're all ready to roll. So let's talk a little bit about a couple of modes. So we sort of have a choice here. Originally, I kind of set it up only with this augmented mode, and then I realized, well, that makes it hard to understand exactly what's going on. So I have a strict mode. So the difference between the two, the prompt is almost identical. But what we do is in strict mode, we tell the LLM, you are to use only the context information that we give you from the vector database. You are not allowed to think on your own. We're only going to use the LLM in this case for its language processing ability. We want it to ignore any knowledge it has because we're using a 20 billion parameter model. Does it have a lot of information about the HP, 2755 inkjet? Hard to know. So we're going to say, we don't want you thinking. We only want you to use the documents we give you, answer the question, answer the ticket based on that. So why would we do that? Well, let's say we're in a case where compliance is critical. There's rules. Maybe we're looking at medical prescriptions. We don't want the LLM freelancing on us and making up answers. We want it to answer from a strict knowledge database. So there are times when you really, really want to restrict it. So this reg mode being strict, all it's doing is altering the prompt to the LLM to restrict what information it's using. The reason we're using it here is we want to QA our answers. How we want to QA our vector database. Do we have enough information in the database to reasonably answer questions? So we'll ask it a question that we know is not in the database because we're going to make it up ourselves, and then we'll see how well it answers. The other I called augmented, and what this means is the LLM is, we tell it to strongly prefer using the data that we provide, the context that we provide, but we don't totally restrict it. This would be helpful maybe where there's only 1 or 2 tickets about a subject or we're slightly off base. It will try its best to answer using a combination of the knowledge that it has, the knowledge that we give it. So again, I would probably not do this unless I was using a pretty big LLM that's more likely to have good knowledge of random stuff. Personally, I've used the big LLMs for support myself. Um, and I would say that it's usually pretty good, but there are times when it takes you down a rabbit hole and it really doesn't quite know what it's talking about. So you definitely want to be very careful about this. What you're trying to accomplish is definitely, definitely needs to be considered. Again, if you're telling people what medication to take, you probably don't want to do this. If you're doing anything where you're going to get sued if it's wrong, you probably don't want to do this. If you're a lawyer who's going into court uh, and representing that this is your own work, you probably don't want to do this. There's lots of reasons why you don't want to do this. Sometimes it's okay. Again, I would probably lean towards using the biggest, most up-to-date models and so on. So it's pretty easy. We've got a config. We can switch between these models. Pretty straightforward. And again, it's pretty straightforward. Either we're going to use the tickets that we've vectorized, or we're going to use tickets plus the LLM knowledge. So the other thing is sometimes you want to make sure that whatever you provide to the user is traceable and explainable. And if you go with the strict, it's pretty easy to point them. You can literally give them the tickets that you're using as a reference. So if they say, why are you saying that? You can say, here are the 9 tickets that I'm relying on to give you this answer. If you use the augmented reg, you can't do that anymore. So there you go. So here we have our code for searching similar tickets. Again, we take the query. So the inputs are what's our query, what's our top K, that's how many tickets will be returned. We've got it defaulting to 5, but we can change that in the function call, and we're going to return a list of the tickets that are returned. Very easy to do. The first thing we have to do is we have to use the same embedding module to encode the query into a 384 dimensional vector. And then we get the results by sending that embedding into the database with the top K, and it'll return that many results, assuming there's that many available. And so then we can peel those apart. We can actually return the distance and the similarity. The similarity is basically 1 minus the distance, so not too much there. But the document that comes back is really, that's the important part. So we get an ID, a document, we get the metadata. Again, we're not going to use that today. We get the similarity, and then we can return that. So generating an answer is simply we're going to take the tickets that we got back. We're going to take the question that the user asked. We're going to set a temperature, which is going to default to 0.2. Remember, lower temperature means less creativity. So in the homework, I'll ask you to experiment with some different temperatures to see if the results get better, worse, or crazy. And then we're going to wrap that into a prompt. So the context, we're going to paste all of the tickets together and create a context by joining all of those together. And then note here, we check to see if it's strict or augmented. That's going to change our prompt. So if we're strict, it's going to say you must use only the user information from the historical tickets. Do not use any external knowledge. If it's not strict, if it's augmented, then it's free to use its own knowledge. So that's pretty straightforward. So again, we just have a template here. We take the context. Here's your context. Here's the new question. Here's your instructions, and then put the answer at the end. So if it's augmented, it says generate a clear and helpful answer to the question. So same basic idea, same template, just a slightly different prompt at the top in terms of what it's allowed to do. We then use our call LLM stuff, our chat completions. It calls the model with the temperature we set, etc., and then it returns an answer. Then we calculate a confidence score. I have kind of a simplistic confidence score. It takes the weights of the first 5 tickets and kind of multiplies them. It kind of weights them, in order. The top ticket's worth 1. The second ticket in line is 80%, 60, 40, 20. And then it kind of computes that. It's kind of a trivial way to compute confidence. And then we craft the answer ticket based on all of this. And we do the answer. We call the function above to generate the answer. We calculate the confidence. We wrap it all together with the references, and we return the response. So we'll just compile all of that. Okay, so we're going to set our mode to strict, and then we're going to create an answer. So here's our right in here. We just created a manual ticket. Very simple. You can go in here and change this to whatever you want. There's lots of stuff. I mean, this database has stuff about a lot of different products. You can ask it, certain things. So here we're just saying, I can't connect to VPN from home. We're not even specifying a product. We're just saying, I can't connect. So here's our ticket. It found 5 similar tickets, but you can see the confidence is pretty low and the similarity isn't great. And in fact, the answer is I don't really have enough information because there's just not it's too vague of a question. That's perfectly fine. Now we can rerun this by switching our mode to augmented. We'll just go back up here and run the same cell. And it's thinking, and we'll see what kind of answer. Okay, so we've got a little bit of a nicer answer here. It didn't really fill this in over here, but it gave some generic advice. Make sure you're entering the correct host name, disable firewalls, confirm that the required port is available using Telnet, try a different device, reinstall the VPN client, clear any proxy settings. So this is very generic advice about how to troubleshoot a VPN connection. It seems helpful. If you're still stuck, give me more specifics. So, basically the same. It's returning the same tickets, so we can guess that it's really using its generic LLM knowledge to answer this question. Now, if we use the tickets that are in the system, I'm going to go back up here and set this back to strict. So I've created another call to the LLM that will compare the answer that we generate against the original ticket answer, which we have in our CSV. So we have the original answer. We're going to generate an answer. We're going to score that. We're going to ask the LLM, we'll give it the 2 answers. We'll give it the question. We'll give it the 2 answers. And we'll ask it to please score those. So that's the function here. Pretty straightforward, just a simple prompt with 2. Here's the question. We're going to give it the original answer from the CSV. We're going to give it the generated answer. We're going to tell it how to score it on accuracy, completeness, helpfulness. We're going to give it a score, and then return that. So we'll compile that. Double check we're in strict mode. So we're going to look at, I checked this is in the test set, not in the training set. So we're going to have it do ticket 380. Here's the ticket body. I have a persistent problem after the latest software. It has to do with Microsoft Excel 365. It crashes. So here's the original answer. Thank you for reaching out, yada, yada, yada. Open the control panel, select Microsoft Office, click change, choose quick repair. That seems pretty reasonable. That's what a human wrote back. Here's what our LLM created. It did a markdown format, and it gave steps. It showed step 1, choose quick repair, verify that the settings are correct. Here it gives references to which tickets it's relying on of the 5 that were returned. Disable all add-ins, run Excel in safe mode, clear temporary files. If it's large, try splitting it. So it gave a few more possibilities. Then we submitted it to be scored, and it gave 5 out of 5. Wow, with a 90% confidence. And this was this was using strict, so that's pretty good, I would say. The LLM evaluation, the generated answer accurately reflects the troubleshooting steps from the original response and expands on them using additional useful actions. The table format makes it easy to follow. It covers all key points and adds extra detail without introducing errors. Not bad. Let's go back and just change to the augmented mode and see if that really changes anything. So we'll rerun this and see if augmented mode makes it any better. One interesting thing is the original language was Spanish, so we're using an English translation. So here's the augmented mode. Well, it used icons a little bit to mark out the steps. It kind of reorganized things a little bit. So first it said repair office and gave step-by-step how to repair and why this is helpful. It verified verify updates, 2 steps, safe mode, 2 steps. So it looks to me like maybe one additional thing, create a new Windows user account. I don't remember that from before. The confidence score is 90%. It's all 5 out of 5. Troubleshooting, it added a couple of additional details. It gives a nice clear. Now, one thing I will note, it dropped the reference to tickets. I guess that kind of makes sense because now it's using its own knowledge. So I guess it can't really refer to specific tickets anymore. Right? So kind of makes sense. I like it. I mean, that's a nice format. I guess if I got that back from an automated system, I'd feel pretty good about it. It seems right. The evaluation looks good. But it's still grounded more or less in the previous tickets. So then I've got a batch evaluation where we can run multiple tickets and kind of figure out, get a little bit better sense. It's basically just looping through multiple tickets in the test set. So it's going to test 5 tickets. Randomly, it shows 622, 87% confidence, ticket 555, 89% confidence. Again, it's telling us it's using augmented mode. Looks like it's taking a couple seconds to answer each one. That's not too bad. Remember, one of our original criteria was that we could respond to users much faster. So, obviously a human would take time just to type out an answer, whereas this could potentially be responding in a few seconds. 82, 85, 82, and the last one, 90. Overall, looks like we're not 5 out of 5 for everything. Completeness, 4.8. I think that feels pretty good. Average confidence, 87%. Again, we have top case set to 5, so it's going to use 5. We can see what languages were used, English, German, Spanish, German, the subjects, the score, the confidence. Seems pretty good. Seems pretty good. I like it. Feels like we made some progress today. So just to kind of wrap up in the last couple of minutes, we built on our previous work. This is all basically reusing a lot of the code. There's a lot of code in this notebook, but keep in mind a lot of it is reuse from weeks 2, 3, and 4. We added the training test split, the confidence scoring, and the LLM evaluation. So we're making use of LLMs in several different ways here. We're translating to English. We're answering the prompt. And we're using the LLM a third way to evaluate the completeness and the quality of the answers. So we're really leaning on the LLM pretty heavily. One thing to keep in mind, we're using OpenAI's GPT OSS 20B, a smallish model, 20 billion parameters. We could easily use a different model for each one of these steps. So if we really want to put this in production, maybe we want to use the real OpenAI GPT-5 for its absolute most up-to-date, most complete answers, etc. So that may be something we try to see if that improves the quality of the answers. We might use that instead as our evaluator because we want the best possible evaluation of our work before we go into production. We might also want to use the evaluation step always, because we might want to look at that as a final step in the pipeline. Before we send the answer back to the user, we want to do a QA step on the answer. So we want to use kind of an independent LLM to judge our answers before we embarrass ourselves by sending something stupid to a user. Not a bad idea. Not a bad idea. We want to make sure we don't have Mecha Hitler answers like Grok famously had a few months ago. And in fact, in a future class, we're going to talk about security and safety guidelines. There are specialized LLMs that will look to make sure we're not using naughty language or stupid or offensive thoughts. When we answer a question about a technical support issue, we should not be referencing Hitler, probably. So we can definitely, there are times to reference Hitler, in historical context, but when answering IT questions, that's probably inappropriate. So now we've got kind of a complete RAG pipeline that loads our ticket data. It creates a vector database. It can answer a random ticket. So we've got at least a kind of let's call it a minimum viable product, a minimum viable offering that does all of the things that we set out to do. Here's stuff that we used from previous weeks. We translated individual tickets to English in our translate tickets.py. We consolidated multiple LLM calls like week 3. We used RAG like week 4. So we combined all these into one application. So in the future, we'll look at using metadata, like the type. Maybe there's reasons why we want to add priority to our search in the database. We want to narrow our focus. Let's say we have 100 tickets that we could use for context. Maybe we want to filter those down. So we want to use tickets that are of similar type, priority, and queue. Maybe that'll get us closer. Maybe that'll up our confidence. We're going to add a re-ranker next week. So we'll show you why that's a good idea and what that does and what those models do. Again, it's just a specialized model. It's very similar to an LLM, but it has a specific training and a specific purpose of re-ranking vector database returns. So the hybrid search is combining the vector similarity semantic search with keyword matching. Talked about that already. Ultimately, at the very end of the pipeline, we'll want to retranslate back into the user's language. Note that we're tracking what language the ticket came in. So for ticket 539, before we send it back to the user, after we do all of our processing, we're going to translate that back to German before we send it. So we've got lots of work left to do, but we're making progress. We've got sort of this MVP now. And then here's what all the files are in the week 05 folder, kind of a list of the files. Here's how to set it up and run it. And here's what the main parameters are. So basically what I want you to do is just play around with this, see if you can get it working. For homework, test out different levels of top K, test out different temperatures, see what the results are like, play with it, and then, up the evaluation at the end, run 100 tickets, run 50, see with these different, experiments, see if you can find a sweet spot between temperature and number of tickets, see if you can goose that confidence level up a little bit. And then when you feel like you are, run 20, 100, and see if it holds. So that's what I've got for this week, guys. Any questions?
Nope. Great session as always, Tom. Thank you kindly.
All right. I think I made it through without brain fog. So the extra week paid off. Great. Well, we'll see you next week. Again, we'll look at some more features like re-ranking, hybrid search, and things like that. We'll keep refining this app until we can. I think maybe in about 6 weeks we should be ready for an IPO. Based on the way things are going in the market right now, I think we could easily go to market with an IPO. So we'll just attach it to Jira. We'll make it an add-on to Jira and automatically add auto responses to Jira trouble tickets. So get ready to be multimillionaires. That's all I'm saying. All right, guys, we'll see you.
Interestingly, had a demo from our infrastructure guys yesterday using Claude Code, where they were picking up a ticket, going in, figuring out what the problem was, creating a branch and a pull request, generating all the code, and then deploying it into an environment for somebody to check. So from
Awesome.
ticket to deployed code without a human being involved. It's a little scary.
Yeah, I think I might want a human in the loop there somewhere, but that's cool. You'll end up with a Jira system at some point that cannot be turned off and just starts modifying all the code in the company database to start creating a giant virus to spread Jira throughout the world, so that the only thing that'll be running on any device is some version of Jira. Cool. So give things a try, play with the code, walk through it. I didn't go into extreme depth on every line of code. I assume you guys can read it yourselves. So have a great day, and we'll see you next week.
Bye, everyone.
Cool. Thank you, Tom.
Thanks, Thomas.
All right. Bye-bye.
Bye.
Bye.